The ideal fabric happens to be a fabric which has fixed finite interface bandwidth, it has zero interface to interface latency, and it has infinite internal bandwidth. It turns out that QFabric is very, very close to an ideal fabric. So what are the properties or the characteristics? Number one is any-to-any connectivity with fairness and full non-blocking. What any-to-any connectivity means is that any set of interfaces can talk to any other set of interfaces with no restrictions and no pre-planning. Next one is low latency, low jitter, and slow latency growth. What does low latency mean? Well, first of all, we can't get zero latency because speed of light has finite value. Okay? 186,000 miles per second. Very fast, but still finite. And at the speeds we're talking about, you end up with some non-zero latency. Low jitter. What's this jitter term? Well, if I plot latency, latency actually turns out to be something in microseconds. If the latency is a few microseconds, it's obviously going to vary a little bit from packet to packet. What we're saying is that the variation is really small. Let's put a number 2 microseconds. What is slow latency growth referring to? It grows very, very slowly as I grow the number of interfaces to tens of thousands of interfaces and beyond. What does QFabric do? It maintains a nice low latency, which is growing slowly, 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 and as you get closer and closer to saturation, which is completely filling up the entire massive bandwidth of QFabric, now the latency starts to take off. And this is unavoidable given the laws of physics. Third characteristic is no drop under congestion. When I have a congested interface, typically in Ethernet networks and in IP networks, the thing that is done is we do packet drops. When there is a congested interface at a very, very fine grain, what happens is that the system, the QFabric, detects this congestion and it actually informs these ingress interfaces continuously and smoothly to slow down so that the sum of their bandwidths do not exceed the available bandwidth. That's no drop under congestion. Linear cost and power scaling. We are talking all the time about large-scale data centers and data centers that you'll have to increase the total number of interfaces as you add more computers and servers and disk drives. And because you have finite amount of power and finite amount of dollars in your pocket, you can't scale the data center very far. So in order to be able to scale, if I have limited resources like dollars or power, this property of linearity is actually very, very nice to have. The next property is called virtual networks and services. Now, obviously, if I have a data center where two competing organizations are using the same infrastructure, you want to enforce non-leakage of data. You want to enforce some protection. So the requirement of multi-tenancy forces you to have the ability to carve out my resources into pools of various shapes. And notice that these pools include resources outside QFabric. It includes the servers, the storage, the appliances, and the routers that are connected to them. You can have lots and lots of different pools, and fundamentally, virtual layer 2 and layer 3 networks and the provision of services enables multi-tenancy. The last property, which is really, really important is that QFabric appears to be a single logical device, despite the fact that its implementation is modular and distributed. But the software, in fact, the director, makes it appear to be a single logical device. So there you have it, 6 defining characteristics of QFabric. And again, I want to emphasize the point that with these defining characteristics, QFabric comes incredibly close to the ideal fabric.